Okay, so this is actually the first lecture of the course, and we start the most important topic of introduction and overview. This is something which you must learn and understand quite deeply, and if you do that, then you will remember that for perhaps decades. So I will share the notes of this. So you can see the notes here. The subject theory of mechanisms and machines has two broad aspects of study. One is analysis and the other is synthesis. Analysis is to find out how a mechanism or a machine behaves. The mechanism or the machine, the device is already known and its behavior is to be studied. Behavior in what sense? In several senses. First, how many degrees of freedom it has? What are the ranges of motion? There is mobility that it can execute. And then when the input quantities are given certain values, there is some actuations are given, then what would be the displacement or positions of several links and their important points? What will be their velocities? What will be their accelerations? And then finally dynamics. That is what actuation forces will cause the mechanism or the machine to support what loads and execute what motion. This way or that way. Okay. So in synthesis, you basically try to devise the system, devise the device. Okay. So the first device is with S, the second is with C. First is the verb, second is the noun. So you have to devise a device for the particular kind of behavior. In this, the behavior is known, behavior is given, and you have to work out the system. You have to work out the mechanism or the machine. Now, in that, some part of this design process is dependent on solid mechanics that we are not going to study in this course. In this course, we are going to study the geometric part of the design, that is kinematics. And synthesis, that is design of a mechanism, involves several things. One is type synthesis. What kind of mechanism it will be? That is, whether it will have gear transmission, whether it will have cam mechanism, or if not, if only linkages, no cam, no gear. Then also you need to decide what kind of joints there will be, spherical joint or sliding prismatic joint or rotary revolute joint or whatever. All these things come into the aspect of type synthesis. This is something for which you cannot do a quantitative study. This typically you decide based on your sense, your understanding as an engineer. That point onwards, the rest lends itself to quantitative study. Numbers, how many links and joints it will have. And after deciding that, you can work out, you can do the dimension. That is, what will be the dimensions of different parts. And this will involve the maximum amount of work. What kind of methods we will apply? We have on one side graphical methods which are conceptually very rich. On the other hand, limited in their scope. On the other side, you have analytical and numerical kind of methods. Basically analytical, and where analytical methods end, that is up to which point you can go analytically, beyond that it will be numerical, which means that iterative algorithms may be needed to be employed. This actually requires that understanding that these graphical methods may be. And there we can also solve problems by a mix of the two kinds of methods. And my favorite way of solving big problems is to think graphically but do the work analytically and numerically. So that way, the conceptual basis of the way I try to solve problems, they are mostly graphical in their spirit. The thought process is graphical, but the actual work is analytical. And I will illustrate, and you will find that is the most efficient way of doing things. Though that is not how things are systematically taught. But this mixed method, think graphically, solve analytically, think graphically, work analytically. I mean, this is something which is actually analytical work, but that is how the analytical work can be, analytical numerical work can be done most efficiently. Now, we are telling all the time that the subject is theory of mechanisms and machines. Now, what is a mechanism and what is a machine? The formal definitions talk of a mechanism as a device for transmission of motion. Now, transmission involves both transfer and transformation. Transfer from one point to another, and transformation from one kind of motion to another kind of motion. And here it is basically talking about transmission of motion. Whatever forces are involved or whatever forces are to be applied, that is not considered in this step. That means that when the focus of the device is the transmission of motion and not botheration about forces, then you call the device as a mechanism. I mean, forces are involved, but they are typically insignificant, very small. So, watch mechanism, steering mechanism. But when the forces are quite important, like in engines, etc., then you talk of machines. And device for transmission of, that is, device for transmission of force and motion. That is transfer and transformation of force and motion. In brief, you can say machine is a device for transmission of mechanical energy. So when you transmit mechanical energy, you end up transmitting both force and motion. Now you see, a machine is for transmission of force and motion. Mechanism is a device for transmission of motion only, though there will be some force. What will be the device which is for transmission of forces only? And whatever little minor motion may be there or may not be there, that is insignificant or should not be there for that matter, that device is called a structure. So if you try to make something as a machine, but it turns out to have degree of freedom 0 or even less, then it ends up being a structure. It cannot move. So stays in the same configuration also. So that is a structure that you study in depth in solid. Right? So, we proceed. Now, graphical methods, as I have told you earlier also, are extremely important, for which you must have constant access near your fingertips geometry box. Now, these basic geometrical constructions you must be very clear with. For a line segment, what is the correct way to bisect, trisect, or make n sections of a line segment in equal sections? So there are standard methods which you learned in school. Bisection of an angle, and you don't talk of trisection of an angle because geometric construction methods for trisection of an angle do not exist. Now, this is one very important construction that for our graphical methods of mechanism. That is circular arc or line and arc intersection. So on one side an arc and the other side a circular arc or line. So both of them can have two possible solutions. Right? So this is very important, and this is in another way you can see it as a dyad. Dyad is a little piece of a mechanism which has two links connected in between with a revolute joint or a prismatic joint. So, for example, say APB. AP is one body, PB is another body, connected together at point P by revolute joint or prismatic joint, rotary or slide. So, if it is rotary, the way this figure shows, then APB, that angle is variable. So, and then there are two given points A and B. Now you have to assemble this dyad, this little piece with two links with a revolute joint in between. You have to assemble it to the main mechanism in such a way that point A of this falls on point A of this, point B of this falls on point B of this. And for that, the system is very simple. You put your compass here, draw a circular arc with radius AP, put your compass needle at point B, draw another circular arc with radius PB, and wherever they cut, that is the point P in the assembly. Right? So this is something very important. And if the in-between joint happens to be sliding, then also the construction is similar. Syntax is here. The next set of constructions that quite often will be needed will be construction of triangles. And each kind of set of data with which you can construct a triangle basically is coded in terms of congruence of two triangles. Okay. And you know SSS, that is, if three sides of one triangle are same as three sides of another triangle, then the two triangles are congruent. This you have studied as congruence theorem. But that also means that if three sides are given, then you can construct a triangle. You put one side and then draw circular arcs with radii equal to the other two sides. Wherever they cut, there is a third vertex. Similarly, SAS congruence result gives you another scheme for triangle construction with two sides and into triangle. ASA or SAA congruence rule gives you the working rule for triangle construction, for which two angles are given and the side is. So ASA is to be made like this. SAA is to be made in slightly different way unless you try to get the third angle by subtracting both of the given angles from one angle. But you don't need to do that. You can make this side, you can make one of the angles and draw this line segment, and then over this you can draw the other angle which is supposed to be here. Draw this, and then parallel to this you draw this final side and final element. RHS is the other congruence rule, that is right angle, hypotenuse, and one side. Okay, so there you use the theorem, fundamental theorem of circles, that is the angle of a semicircle is right angle. So you draw the hypotenuse and take that as a diameter, make a semicircle, and then cut the length of one of the side given sides, and that's the third one. SSA you do not have as a congruence. Two sides and an outside angle. For that, congruence rule is not there because there is an ambiguity. For example, say this side is given and this side is given, BC is given, AC is given, and angle C is not given, but angle B is given. So for that, the ambiguity comes because you can draw the angle B, get this BA line, but you don't know where it is, where the point A is. Then with AC, as you draw the circular arc, it may cut the BA line at two points, here and here. Both are valid so far as the data given is concerned. So which is valid in a particular context, or whether both are valid, has to be figured out from something else given in the problem. Okay. Now, this ambiguity arises only if the angle B is an angle. That is really interesting. You should try to find out. Okay. Now, the method to draw the tangent to a circle from a point on a point given on the circle, that's very simple. You draw the corresponding radius, make a right angle, and that is the tangent. From a point given outside the triangle, outside the circle, that is not on the circle, then you join the point with the center of the circle, then use that same thing as you used here, that angle of a semicircle is the right angle. You need a right angle here, so use this as a diameter and make a semicircle. Wherever it cuts the circle, that is the point where the tangent will touch. Common tangents to two circles. And now, here I find many students trying to do it by fitting. One circle is here, another circle is here. Sometimes people try to take the scale or the ruler and try to do it like this, like this, like this, like this. Don't do that. That's not the method. The method is to say the two circles have one bigger, one smaller. If the two are same, then it is easier. Okay. So one bigger, one smaller. So first, take the difference of the two radii. Okay. That is R1 minus R2, and with that radius, draw a circle. Okay. That means you are shrinking this bigger circle by the radius of the smaller circle. And with the same, you shrink this also, then this gets shrunk to a point. Okay. Then from the point, you draw tangent, one here and one here. Okay. Once you have done that, then you move this parallel to itself to touch here and here, like this. That is directed. Another will be parallel to this. That is like this. Like this. That will be directed. And for that, the way is easy. You this tangent, wherever it touches, that point and the center you join and extend. And parallel to that, you make this, and wherever that cuts here, so wherever the two perpendicular lines cut this circle and that circle, you join those. Similarly, on the lower side. This will be the pair of direct angles. For the cross tangents, rather than taking the difference of the radii, you will take the sum of the radii and make a bigger circle. And then you have this center to the bigger circle, R1 plus R2 circle, and then move it like this by making right angles. Okay. This will be directly connected, okay, to the center. That will be the right angle. Okay. And here also parallel to that you make wherever it cuts. So this will be one tangent like this, and similarly another tangent will be moving this parallel. So this is the method. This is the correct way. Now, the way we talked about triad assembly, some people try to do triad assembly, which is impossible. So I have seen students facing a problem with a much bigger mechanism, having lots and lots of links. Then they find that they have got in hand a little piece of the mechanism, A prime P, PQ, QV prime. Okay. 3 links, not 2. And then point A prime has to be put at A, point B prime has to be put at A. This much is. Then I have found students some students putting A prime at A, draw an arc, circular arc with AP radius, then putting B prime at B, draw another circular arc with BQ radius, and then they know that P will be on this arc, Q will be on this arc, and then they take their scale and PQ length they know, they try to fill it like this, like this, like this, like this, wherever it fits. But this is a very, very dangerous way to try to do. This is doesn't. Okay, and you will end up doing, I mean, it is first of all not a method. Second, it will be very clumsy. And third, it may introduce gross inaccuracies. Now, the simple point is that right now you only can fix the locus of P, locus of Q as circular arc and nothing more. You will need to find out something else from some other part of the mechanism to fix either P or Q in a different, coming from a different branch of the mechanism. Then only you will be able to fix everything properly. Otherwise, it will give us a lot of inaccuracies, and later, at a later stage, you will find that something is impossible. Okay? Something is just not fitting. It will be wrong. So be careful that you don't do that kind of. Don't even try such shortcuts. Now, that kind of situation may arise in complicated geometric construction, for which what is given and what is not given, what is required, I mean, they will be enmeshed in such a manner that it takes some amount of thinking to work out the sequence in which you can position the point. For example, Suppose you want to construct this figure with all the linear dimensions here that is visible to you, that is connected, unknown. That is AB known, BC known, CD known, DE known, then DG known, EF known, FG known, FH, GH, HI, these are known. Okay. And these four angles are known. And this angle, this angle, this angle, and this. This much is known. BI is not known. AE is not known. So whatever is not drawn, that is not known. Okay. And this angle, angle BEF, angle BEF, that is not known. So now, how to construct that? With these things, no, whatever is visible in the drawing. So, one possible sequence of locating the points on paper could be, and equivalently in a computer program, could be first locate B and C, because I mean that is basically the position of the entire diagram in the on the paper, right? In the entire paper. So that much you can anyway do wherever on the paper you want the figure. So B and C you put first, and then one possible way to do it. Right now you cannot fix G, but you can fix B, and you can fix A because these two angles are B. So after fixing B and C, by making this angle and using the length AB, you can fix A. Once A is fixed using this angle and this length, you can fix R. But now you cannot fix A. So you have to stop. Okay, you have to wait and try to get hold of something else. And something else is this angle BCD. Making an angle BCD and using the length CD, you fix D. Once you have fixed D, then you say what? What else I have, what else I don't. Okay, angle D. So you make angle D and then fix G. That is why after fixing B, C, A, I in this branch you stop and then go up on this branch, fix D, then G. Once you have fixed G, then you have got a good handle. Now you see diode assembly you can do, and I you know, G you, and the length IH, length GH, there. Okay. So then with two circular arcs cutting at H, you get hold of it. And here actually you have to decide whether H is here or here, because two circular arcs can cut at 2 points. Okay. So after fixing H, you see what else can be done. Now G has been already fixed, H has been fixed. A triangle is a rigid structure, so F gets fixed. After F has been fixed, finally you get E, because this is again a diode. So at every stage, you are actually fixing up a diode. So the order can be B, C, A, I, then B, G, H, F, E. In this sequence, this is one possible sequence in which you can fix all the points and therefore complete the diode. Now, mirror images in some cases will matter, in some cases will not. And that information you will get from some extraneous consideration. So, for example, FGH, okay, whether FGH is counterclockwise as appears in this, or clockwise, that is, if F had one on that side, then it would be clockwise FGH. So, mirror images in some cases will matter. In this case, it seems to be doing it. Now, regarding the triangle construction thing that we were discussing earlier, the little summary is given for you. what is meant by these construction of triangle formulations. These are the different cases. And as I told you that in the SSA case, you have ambiguity. Okay. But ambiguity is only when uh, the angle is less than ambiguous. Okay. Now, in any of the cases, it can be that the construction is impossible. If the two arcs don't come, then what can it be? Okay. So such cases would be possible here also. Okay. For example, three sides are given, but they are funny. One is 3, the other is 5, the other is 10. So that triangle cannot be constructed. So impossibility is always there. Here it quite often comes. So if the given angle in the SSA case is acute, then either it is impossible or it is just two solutions. I mean, so the solution is not determined does not mean that whatever is possible. No, just two solutions. Ambiguity. On the other hand, if the given angle is a right angle or an obtuse angle, then if it is impossible, it is impossible. Fine. If it is possible, then it will be unique. Because if it is equal to the entity, the given angle is a right angle, then two possibilities are there. But there is no ambiguity because the two possibilities are the same. One is the mirror image of the other. If it is obtuse angle, 110 degree, 120 degree, something like that, then only one possibility is there because the arc intersection will give you two intersections, but one of them will not give that obtuse angle. That will be on this side, and that the given angle will turn out to be active. Okay. Rather than 120 degree, the angle will appear as 60 degree. So it will be automatically invalidated. So you should verify all these things once quickly. In childhood, you have once done certainly, but you need to quickly brush up on your own. You don't need any book. That just experiment mentally with a little pencil and paper. Say, okay, I do this, then I do this, then I do this. Oh, so this will do that. So this kind of verification you can do very easily. Now, if all the three angles are, then you cannot construct the triangle because with three angles given, basically you can construct hundreds and hundreds of triangles, all similar to each other. So which one of them is the one that you want? So you will be on the lookout for some data on length of this. Now, here again, make note that mirror images are equivalent in some contexts and in some contexts they are not. Now, all these things, I advise you strongly to verify on your own with some little 2 minute, 1 minute, half minute kind of pencil paper exercise. I mean, mental exercise with pencil. Okay. Or pen and paper also is fine because you are not really doing proper geometric construction. The things that are mentioned on this slide and on this slide, all the constructions, you try to verify on your own. And if something of this you are missing, and you studied for some time back and you have forgotten in the intermediate 5 years, okay, then raise those things in the next discussion hour. So these are the preliminary things. There is graphical tools and handles and the basic terms that we will talk about all the time that I needed to familiarize with you in this particular.